The planet with no sunrise, no sunset. The world that never turns. Imagine waking up on a planet where the sun never rises. Not because it's dark, because it's already up. It's been up for 1 billion years. It will be up for 1 billion more. It hangs in the exact same spot in the sky, forever. Now walk far enough in one direction, and the light fades. Keep walking, and you cross into a night that has never once seen daylight, a night that is, quite literally, older than complex life on Earth. This isn't a thought experiment. Astronomers have found a real planet like this, 48 light-years from where you're sitting right now. And for years, scientists assumed a world like this was one of the least likely places in the universe to find life. New research says they might have been wrong. This is the story of tidally locked planets, worlds frozen in a permanent standoff between fire and ice, and why some of the best odds for finding life beyond Earth might be hiding in the strip of twilight in between. What does it mean to be tidally locked? The Moon is already doing this. Here's the strange part: you don't have to travel 48 light-years to see this phenomenon. You just have to look up. The Moon takes about 27.3 days to rotate once on its axis. It also takes about 27.3 days to orbit the Earth. Those two numbers being identical isn't a coincidence, it's the result of a slow gravitational tug-of-war that's been playing out for billions of years. Because of this, the Moon always shows us the same face. There's a hemisphere of the Moon that no human being saw with their own eyes until 1959, when a Soviet probe finally photographed it. We call it, a little inaccurately, the dark side of the Moon. It's not actually dark, it just never faces us. This state is called tidal locking. And it's not rare. It's not even unusual. In fact, once you understand the physics behind it, you start to realize it might be the default setting for most rocky worlds in the universe, not the exception. The physics, without the math, here's how it happens. When one object orbits another, a moon around a planet around a star, the gravity of the larger body doesn't pull evenly. It pulls harder on the near side than the far side. That stretches the smaller object slightly, giving it a subtle bulge, a bit like squeezing a stress ball. If the smaller body is rotating faster than it's orbiting, that bulge is constantly being dragged out of alignment, and friction inside the object slowly bleeds off its rotational energy, like a brake being gently applied, over millions of years. Eventually, the rotation slows down just enough to match the orbit exactly. At that point, the bulge locks into place, always pointing at the same spot. And once that happens, there's no more friction left to slow things down further. The system settles. Permanently. This is exactly what happened to our Moon. It's also what happened to Pluto and its largest moon, Charon, except in that case, both bodies are tidally locked to each other. If you stood on Pluto and looked at Charon, it would never move in the sky. Not once. Ever. Mercury's almost locked. Mercury is a fascinating in-between case. For decades, astronomers assumed Mercury was fully tidally locked to the Sun. Turns out, it's not. It rotates 3 times for every 2 orbits it makes. A near lock, thrown slightly off balance by its unusually elongated orbit. It's a reminder that tidal locking isn't always a clean, perfect state. Sometimes it's a messy equilibrium, and the details matter enormously for what the surface conditions actually look like. Why this matters for planets around other stars, now here's where it gets important. The kind of star a planet orbits changes everything. Most stars in our galaxy aren't like the Sun. The vast majority are red dwarfs, smaller, cooler, dimmer stars. Because they're dimmer, a planet has to orbit much closer to a red dwarf to receive enough warmth to potentially have liquid water on its surface. But orbiting close to a star means stronger tidal forces. And stronger tidal forces mean tidal locking happens fast, often within just a few million years, which is essentially instant on cosmic timescales. So here's the uncomfortable truth for anyone hoping to find an Earth-like world with a nice 24-hour day-night cycle. Around the most common type of star in the galaxy, the potentially habitable planets are probably not going to have a day-night cycle at all. They're probably going to look like the world we're about to meet. blank, underscore, blank, meet LHS 3844b, the planet with no sunset discovery. In 2018, NASA's TESS mission, the Transients Exoplanet Survey satellite, was doing what it does best, staring at nearby stars, watching for the tiny, telltale dip in brightness that happens when a planet crosses in front of its star. That's how astronomers found LHS 3844b. It orbits a small red dwarf star called LHS 3844, sitting about 48.5 light-years from Earth, practically next door, in cosmic terms. The planet itself is only slightly larger than Earth, about 1.3 times our planet's mass. If you were designing a planet from scratch to spark curiosity about habitability, you'd probably land somewhere close to this. But here's the catch, LHS 3844b completes an entire orbit around its star in just 11 hours. 11 hours. Compare that to Earth's 365-day trip around the Sun. That's how close it is to its star, and that closeness comes with a price. A world split in two, because it orbits so closely and so quickly. LHS 3844b is almost certainly tidally locked. And that locking creates one of the most extreme environments scientists have ever modeled. On the day side, the hemisphere permanently facing the star, surface temperatures are estimated to reach somewhere between 1000 and 2000 Kelvin. That's hot enough to keep rock in a molten, lava ocean state. Any atmosphere the planet might have started with was likely stripped away or baked off entirely on this side. On the night side, the hemisphere that has never once seen its star, temperatures plunge toward absolute zero. 0 Kelvin. The theoretical point where atomic motion nearly stops entirely. It is, for all practical purposes, one of the coldest places you could imagine, permanently sealed in total darkness. There is no dawn. There is no dusk. There is no yesterday or tomorrow in the way we experience it. There is only here, burning, and there, frozen, and a boundary between them that has stayed in exactly the same place for as long as the planet has existed. Why scientists almost wrote this off. For a long time, planets like this were treated as a footnote in the search for life, interesting to study, but not serious candidates. The logic seemed airtight, life as we understand it needs stability. Liquid water. A survivable temperature range. A planet split between a lava ocean and absolute zero seemed like the textbook definition of not that. But there was a problem with that reasoning. Scientists were only really looking at the surface. They were treating the dayside and nightside as if they were sealed off from each other, two separate worlds glued together by coincidence. Nobody had seriously asked, what's happening underneath? That question is exactly what a research team led by Daisuke Noto, a postdoctoral researcher working out of the University of Pennsylvania's Penn GEFLOW lab, decided to chase down. And what they built to answer it might be the most low-budget, high-impact planetary science experiment you'll see this year. Blank, underscore, blank. The lab that built a fake planet building an actual exoplanet wasn't in the budget. You can't fly a spacecraft to LHS 3844b. It's 48 light-years away. Even our fastest probes would take hundreds of thousands of years to arrive. So if you want to understand what's happening beneath its crust, you have to get creative. Noto and his collaborators, working with researchers at the Japan Agency for Marine Earth Science and Technology and Hokkaido University, built something almost charmingly low-tech, a tabletop rectangular tank filled with a thick, syrupy liquid called glycerol, seeded with thermochromic liquid crystals, tiny particles that change color depending on temperature. Around the tank, they installed 4 separate thermostats, each one capable of heating or cooling a different region. It let them recreate, in miniature, the exact kind of temperature extremes you'd expect between a planet's permanently lit side and its permanently dark side. As Noto himself put it, and this is a direct paraphrase of his own dry sense of humor about the whole setup, building an actual exoplanet clearly wasn't going to happen on a university research budget. So they built a working analog instead. Why glycerol, and why it actually works? This might sound like a strange substitute for a planet, but the physics holds up better than you'd expect. A planet's mantle, the thick rocky layer between the crust and the core, doesn't move like ocean water or atmospheric wind. It moves the way thick, viscous fluid moves, slowly, driven almost entirely by differences in temperature and density, not by rotation or weather patterns. Earth's oceans and atmosphere are dominated by the planet's spin. That's why we get things like the jet stream and rotating storm systems. But deep mantle convection barely notices rotation at all. That means a slow, viscous fluid like glycerol, sitting in a tank, heated unevenly, is actually a reasonably faithful stand-in for what's happening in the rocky interior of a tidally locked world. It's the same technique researchers have used for decades to study convection in general. Noto's team just pointed it at a very specific, very extreme planetary scenario. What they found, here's what happened when they ran it. Hot material rose on the side that was heated, the equivalent of the day side. It flowed laterally across the top of the tank, gradually cooling as it traveled, and then sank back down on the cold side, the equivalent of the night side. Then it looped back around and did it again. And again. And again. Not chaotically. Not randomly. In Noto's own words, describing the pattern, the convection was slow, steady, and predictable, nothing like the turbulent, constantly shifting mantle currents we see modeled for Earth. This was closer to a single, stable, continuous loop, locked in place, just like the planet itself. More striking, the experiment revealed stationary hot plumes, concentrated columns of rising heat, fixed in one location, similar to the hot spots that create volcanic island chains like Hawaii on Earth. Except on a tidally locked world, these plumes wouldn't wander. They'd stay anchored to the same spot, potentially for the planet's entire lifetime. The domino effect, volcanoes, magnetic fields, and habitability, this is where the implications start stacking up. If heat is being funneled through fixed plumes toward the day side, that suggests concentrated, possibly intense volcanic activity in specific zones, rather than volcanism scattered randomly across the whole planet. And if the mantle is convecting in this steady, organized way, it could also be doing something else, stirring the planet's liquid core. On Earth, that kind of core convection is exactly what generates our magnetic field, the invisible shield that protects the surface from being stripped bare by solar radiation. Noto's team hasn't tested this part directly yet. It's a hypothesis built on the pattern they observed, not a confirmed result. But if a tidally locked planet like LHS 3844b can generate its own magnetic field this way, it could mean something previously written off as inhospitable actually has one of the key protective ingredients life needs to survive long-term exposure to stellar radiation. Blank, underscore, blank, the twilight zone, where life might actually hide, introducing the Terminator. Between the blistering day side and the frozen night side of any tidally locked planet, there's a narrow ring where neither extreme fully wins. Astronomers call it the Terminator, the same word used for the day-night boundary line that sweeps across Earth every 24 hours. Except here, it doesn't sweep anywhere. It's frozen in place, forever, as a permanent ring of twilight circling the planet. For years, this Terminator zone has been the leading candidate for where life might exist on a tidally locked world, a kind of narrow, ring-shaped Goldilocks zone, wrapped around the entire planet rather than stretched between two entire hemispheres. It's not just the Terminator, it might be the whole planet, but newer atmospheric modeling suggests the Terminator might not be the only game in town. Researchers like Dorian Abbott and Daniel Cole have shown that if a tidally locked planet has the right kind of atmosphere, dense enough to move heat efficiently, but not so dense that it becomes a runaway greenhouse, that atmosphere can carry warmth from the day side deep into the night side, and pull cold air back the other way. If that balance is right, habitable conditions wouldn't be squeezed into one thin ring. They could be spread much more broadly across the surface, a delicate, planet-wide circulation system doing the work that a day-night rotation cycle does here on Earth. There's a real tension in that balance, though. Too thin an atmosphere, and the night side gets so cold that gases start freezing directly out of the sky, stripping the atmosphere away entirely. Too thick, and you risk the opposite problem, an atmosphere so smothering it traps heat uncontrollably, more like the crushing greenhouse conditions on Venus. Combining the two discoveries. Here's what makes 2026 a genuinely interesting moment for this field. For the first time, we have two independent lines of research pointing toward the same conclusion from completely different directions. One line of evidence, the atmospheric modeling, suggests heat can be spread across the surface through winds, potentially widening the habitable zone well past the terminator. The other, Noto's mantle convection experiment, suggests heat can also be managed from below, through stable convection currents and localized volcanic and magnetic activity that could protect and stabilize conditions in specific regions. Put those together, and a picture starts to emerge that's very different from the half fire, half ice, entirely dead assumption that dominated thinking about these planets for years. Not a hospitable world by Earth standards, certainly. But not an automatic dead end, either. Blank, the bigger picture. Why most habitable worlds may look like this tidally locked worlds are everywhere. If tidally locked planets were rare oddities, this would be an interesting but narrow corner of astrobiology. They're not rare. Multiple lines of research suggest they may represent the majority of potentially habitable worlds in the galaxy. Take the TRAPPIST-1 system, 7 roughly Earth-sized planets orbiting an ultra-cool red dwarf just 40 light-years away. Several of them sit inside the star's habitable zone, where temperatures could theoretically allow liquid water. And because they orbit so tightly around such a dim, cool star, models suggest most, possibly all, of them are tidally locked. Multiply that pattern across the galaxy. Red dwarfs make up roughly 3/4 of all stars in the Milky Way. If habitable zone planets around red dwarfs are usually tidally locked, and the physics strongly suggests they usually are, then worlds with permanent day and permanent night, rather than worlds with a familiar 24-hour cycle like ours, may be the default setup for rocky planets sitting in the habitable zone of their star. Other extreme examples we've already found. LHS 3844b isn't alone. Astronomers have already found and studied several other worlds that showcase just how extreme and varied tidally locked planets can be. Take 55 Cancri, a large rocky planet orbiting its Sun-like star roughly once every 18 hours. Its dayside is hot enough to maintain a permanent ocean of molten lava. Or WASP 121b, a scorching gas giant studied by the James Webb Space Telescope, where researchers confirmed something models had predicted for years: measurable differences between its eternal morning and eternal evening regions, fierce winds physically carrying heat away from the permanently lit dayside, creating distinct chemical and temperature signatures at different points around the terminator. Every one of these worlds is a live laboratory for the same underlying question: when a planet is frozen into a permanent relationship with its star, what actually happens to the climate, the geology, and, potentially, the chemistry of life? Redefining habitable. All of this is quietly forcing a redefinition of one of astrobiology's most fundamental terms: habitable. For decades, the unspoken assumption baked into the search for alien life was that a habitable planet should look, in broad strokes, like Earth. A day-night cycle. Seasons. A rotation axis. A single, more or less uniform climate band circling the globe. Tidally locked worlds break every one of those assumptions simultaneously, and the growing body of research into worlds like LHS 3844b suggests that instead of ruling them out, we may need an entirely different mental model for what habitable can look like. Not necessarily a green, blue, Earth twin. Possibly something closer to a permanent ring of temperate twilight wrapped around a planet that is, by any human measure, hell on one side and a frozen wasteland on the other. Blank, what comes next? What we still don't know. It's worth being honest about the limits of what we actually know right now. Noto's experiment is an analog, not direct observation. Nobody has drilled into the mantle of an exoplanet, and nobody ever will with current technology. The magnetic field hypothesis is exactly that, a hypothesis, built on a pattern, not yet confirmed. And the atmospheric modeling that suggests broader habitability still depends heavily on assumptions about atmospheric composition and thickness that we can't directly measure on most of these worlds yet. Real science rarely arrives as a single, clean, yes. It arrives as a series of independent findings that all start pointing in a similar direction, which is exactly the phase this field is in right now. How we'll actually check, the next real test comes from telescopes, not tanks of glycerol. The James Webb Space Telescope has already demonstrated it can detect atmospheric and thermal differences between the dayside and nightside of tidally locked worlds, as it did with WASP 121b. As observation time increases and instruments improve, astronomers expect to gather atmospheric data, and possibly biosignature candidates, from smaller, rockier tidally locked planets like LHS 3844b. That's the direct evidence that could eventually confirm or rule out everything this episode has walked through. Why this search matters. If it turns out that tidally locked planets really can support life, even in a narrow band, even under extreme conditions, the implications are enormous. It would mean the pool of potentially habitable worlds in our galaxy isn't a small, Earth-like subset. It could be the vast majority of rocky planets sitting in a habitable zone, most of them orbiting the most common star type there is. That doesn't mean the galaxy is teeming with life. It means we may have been searching with the wrong checklist. _blank, why this changes how we search. Somewhere out there, 48 light-years from here, there's a planet where the sun has never once moved in the sky. Where one entire hemisphere has never known darkness, and the other has never known light. For a long time, we assumed that made it one of the least interesting places to look for life in the universe. We're now finding out it might be one of the most important places to look, not despite the extremes, but because of the delicate, hidden systems quietly working to balance them out, deep beneath the surface, one slow convection current at a time. If you want to see where this research goes next, the JWST observations, the mantle experiments, the search for the twilight zones where life might actually take hold, subscribe, and I'll bring you the next discovery the moment it breaks. I'm Sky's Eye. Thanks for watching.